anyone who doesn't speak English at all, you should probably not take this course. It's going to be in English. Okay, welcome everybody. So this is a course on memory management. This is what we're going to do today. We'll start with administration, and then we'll do some overview, and we'll start with the real material probably in the second hour. Okay, so there is a book. It's not a course book in the sense that we're going over it chapter by chapter, but it does contain a lot of the material, a lot of time more deeply than we're going to go through, maybe more algorithms, maybe deeper into systems or architecture, but it has a lot of the material, and you can look at it. These are the authors of the book. These are the people, and memory management in general, it's related to a lot of areas in computer science. It's of course, to algorithms. There are algorithms, and if you do algorithms, you have to understand how to reclaim memory in your data structures. Operating systems, you have to understand some of the stuff of operating system in order to do memory reclamation properly. And, concurrency. Anything that you buy today, your laptop, your desktop, your smartphone, your tablet, they all have multi-cores. They all have concurrency. You can choose to use it or not, but as programmers, you'll probably want to use concurrency in today's computing. So we'll also talk a lot about concurrency for memory management, which makes it harder, and we'll see some algorithms and how it goes. Our focus is going to be algorithms. We'll talk about system requirements, what's the connection to the system and to the hardware, but we'll not focus on system stuff. So sometimes systems people like to say, this is what happens in Linux in 75, and this is what happens in Windows in 95. We only care about the basics and the algorithms, and we'll try to go through that through the course. We'll sometimes, especially in the beginning, we'll talk about engineering techniques. What do you do when you actually have to program stuff in reality, and you have to worry about, execution time, space overhead, and so we'll mention that. It's an applied course. What I mean is not that you have to program and run code, but there are lots of amazing theoretical courses in the faculty, and the nice thing is they can choose what they teach. So they choose the most elegant, beautiful algorithms and teach them. In applied courses, we usually teach you what's actually happening in real life. So there is some dirt, and we have to actually go through all the things that you meet in real life, and we cannot just choose what we like to teach. So you will see here some things that are not purely elegant, but they are what you have to work with in real life. And so this is what I mean by applied course. We will be guided by what happens in the industry and in the real world as we choose what to talk about. Okay. Why is it important? So, when you start to work on computers, on programming, people say, the computers are non-deterministic, they're against me, they're doing strange things. I run it once, it does that. I run it again, it does that. It doesn't make sense. And as you study more and more courses in the faculty, you see that the computer is deterministic, and it does think there is a reason for why things are happening. And you see it through courses that teach you what's happening below your program, right? I mean, you run your program, but things happen while it is running. And there's, architecture with caches that you've seen in operating systems, and, virtual memory. And there's a lot of stuff that happens that may change the behavior of your program. And often it is very good for you to know this and program knowing what's happening below. So, compilers, some of you are going to study in subsequent semesters. Some of you have already studied it. This shows you how your program is written into machine code and then executes on the actual operating system and hardware. And memory management is one of these. You'll see that, if you just change a pointer and sometimes it starts a procedure that's related to memory reclamation. And it's not non-deterministic. There is a reason why things are happening. And you can see it here. Of course, concurrency is something that is good to understand because it creates a lot of problems if you have no idea what's happening there. All of these things are important for you if you want to understand what's happening to your program when it actually executes. Okay, for computing, so memory is the bottleneck. If you run a program, of course, if you go to disks, it's slow and you're aware of it, you read from files, it will take a lot of time. But as you run your program, there's a lot of, it's very important to understand that the memory is the bottleneck and it costs a lot in performance, in energy, and it's good for you to understand and try to save on the memory overhead. It relates to all of the things. So if you're doing programming languages, you have to decide which memory manager you'll use for your program and design your compiler appropriately. If you're doing databases or any stores of data, you have to understand how it is stored, what happens below. Most of your time is going to be on accessing that memory, which is going to take your time. And to software in general, this is something that it will help you to understand. Of course, there's a lot of investment in research and in production, in industry and in academia. And we're going to talk about a lot of this. The way this course is going to run is we'll start with very simple algorithm, almost at the deceiving level. You'll think that everything is really simple and there's nothing to it. It will be a bit deceiving as we go along. It will be more and more complicated. And of course, you will see that if you stay here. So we will do better algorithms. We also try to understand how programs behave, and then we will adapt to that. So if programs do something very often, maybe we can do stuff that for these programs, for most of the programs, will help them to run faster with lower space overhead. So we will work for typical programs. Of course, for platforms, we have this concurrency that we will talk a lot. Because it's important and also because I like concurrency, so you'll see a lot of it. You have to understand, it will be very clear during this course that cache misses are very, very important. The cache, if you can hit the cache and run your program so it can work with the cache without cache misses, then your program will run a lot faster. This is something that is not taught in basic courses in the faculty. Maybe you understand what a cache is, but probably you don't understand how important it is and how much, if you want to get a better performance and have your program run faster with less energy consumption, how much you have to worry about doing things with locality. You have to make sure that things do not touch the memory randomly, but are more local in the computation. We'll talk about that. Real time, if you want to build something for airplanes or for stock exchange and you have to respond quickly to things that are happening, then this is called real time. We'll talk about that, hopefully. We will talk about one theoretical lower bound. I realize that not all of you have studied the computability, חישוביות, right? There are people who haven't, yes. So I'm going to talk very lightly on this and try to explain it, if we have time, of course, because I like it and because there are some impossibilities that are useful to know. You don't want to try and do stuff that cannot be done. Mathematically can be shown to not be possible. So hopefully we'll have time for this. But the focus generally is the basic ideas and which algorithms are used in practice throughout the years and today, and what are the basic ideas that form these algorithms. Okay? Grades. So test is in closed material, so uh, we can talk about it, but I really hate to see tests in which people print these books and then they come to class and drop it on the table and feel that it's very helpful. Usually their parents copy it for them, right? I don't know. It's work for the parents. It's not good for the environment, for Earth, and I don't think it's very useful. If we I think you should memorize for the test anything that takes, a thumb rule would be if I talk about it for more than 20 minutes, then you should remember what it is and what it does. If I mention it, in 2 minutes in the class, then I don't expect you to remember it. I will remind it in the test. Okay, so you don't need open material, but this is how it's going to go. Homework is at least, so this is at least 75%. I will soon say why at least. And also homework is at least 10%, which is clear. There will be 3 homework exercises, no coding, but really to understand what's happening in class. And there is something that's called participation in class. So I want to be able to raise the grade for someone who is really sitting in class and maybe asking very good questions or making very interesting remarks. I want to hear from you. It's okay if you want to be anonymous and sit in your chair and just listen, that's fine. A lot of very good students are like that. But if there are students who really participate, then I will use this item in order to increase their grades. If you're anonymous and not interrupting, then this is going to form your grade. Just blow it to 100 and that will be your grade. So this is the grade. Any questions? Okay. So I cannot spend too much time on, working with students to understand everything that happened in the last lecture. Give you solutions to exams and stuff like that. You have to be independent. There are no exercise and metargelim. There are no TAs, teaching assistants in this course. There is one that is checking your homework and use him to get some feedback. He's very good. He's excellent. Tomer Corey. So you don't have, if you miss the homework and you copy them, you'll have fewer questions to study before the exams. There will be no booklets of exam exercises. So be aware that you have to be more independent. If this is your first elective course, it's very different from what you are used to in the compulsory large courses. Okay, what you do have is you have my lectures here, you have the slides which will be published, and you'll have the homework, which sometimes you think are not good for you, but are very good for you. Any questions about this? Okay, you don't have to come, but it would be useful for you to come. There are prerequisites. There is 2 courses that you have to pass to have a passing grade in order to come to this course, which is Algorithms 1 and Operating Systems. If you don't have the prerequisite, then you should come to talk to me. If you just stay and ignore it, then in the middle of the semester, the administration is going to cancel your registrations. And after you've worked on this course, this will not be good for you. So don't ignore it. If you don't have these courses, if you haven't passed these courses, come to speak to me or, cancel the course. And the course will be run on GR. You probably know it from previous courses. English. So because this is supposed to be a course in English, I will not publish previous videos in Hebrew. This would be kind of funny, and you're not supposed to look for those and try to look at them instead of coming to the lectures. This would be inappropriate. I don't know how the Technion looks at it, but it's clearly not what should happen in an English course. I do not want to anybody to be afraid of asking questions or what will happen in the test. So from your point of view, you can talk Hebrew. I will try to translate it for those who do not speak Hebrew, but you can ask questions here in Hebrew. There's no problem. I will understand and answer in English. You can submit homework in Hebrew, and you can write the test in Hebrew. Okay, so I don't want you to be afraid of the English, unless you don't understand what I'm saying, and then you should be afraid and, cancel the course. But if you understand what I'm saying, then your job is not to be speaking English or writing English. Okay, so this is any questions about this? So I think if you have any questions about administrations at all, then this is the time, or we'll start with real issues. So, okay. So let me first zoom out of, a computer system. First, there is the architecture. You've probably heard about it. There's the CPU does all the computation. There's a memory where you store all the data. And there is a cache that stores your most recently used data so you can access it very fast. This is small and very fast. This is a lot larger and slower. And once you turn off the computer, all of this is gone. And if you want to save stuff for the next time you use the computer, you have to save it on the disk or an SSD. So this is the hardware, and you will maybe learn about it in a course here, but the basic things I think you know already. The operating system, we have three major operating systems that most people are using. It's Windows, Mac OS, and Linux, and they abstract for you all these tiny little unimportant details that the architecture comes with. If you buy an SSD, and in order to write a block into the SSD, you have to write to a specific register the address, and then to another register the content. You don't want to know that. There is the operating systems give you a file system. You open a file, you write to it. Everything doesn't depend on which SSD you chose to buy. So this gives you an abstraction of what's going below. And also it takes care of scheduling tasks and everything else. The application is what you're used to be doing in most of your courses. You write high-level codes, and then a compiler, maybe you use some libraries. The compilers will make it low-level code, and you can run it on your system. The runtime, I don't think you've ever met before this course. So, for example, Java has a Java virtual machine that if you want to run Java has to be installed in your computer. Microsoft has a common language runtime or .NET virtual machine that runs their languages. And so what does it do? So it does memory management. So if you run malloc in your program or you do new for an object, this will be served by the runtime, by the memory manager. And you have a runtime stack where if you go into a method, it will put a frame into the runtime stack and all the variables can be stored there. It has a just-in-time compiler, which probably you haven't heard before. If you run a Java program and you start to execute a loop and you do it million iterations, Java will stop and it will optimize the low-level code for that loop. So when you run it for the next million times, it will run a lot faster. This is called just-in-time compiler. And usually if you talk to professionals, they will say JIT for just-in-time, JIT compilation. And this is an important and hard thing that is happening below your program. So maybe you run a million iterations and they go quite fast, and then a single iteration will take a lot of time. And then the next iterations will run faster. This is because there is a JIT compiler that runs under your program and does these optimizations on code that you run a lot. Okay, and there are threads. Threads usually are run by the operating systems, but sometimes the runtime tries to do better and more. But the two more important things and the challenges in the runtime is the memory management and the JIT, the just-in-time compiler. The compilation you will learn in your compilers course. So I will not talk at all about it, but this course is about the memory management. It's part of the runtime. It goes with when you run a program, this gives services to your program while it's running. And this is what we're doing here. Languages that have automatic memory management are called managed languages, sometimes called managed code. And most modern languages, except for C and C++, basically all modern languages support managed runtimes and automatic memory management and garbage collection. Okay, so what I want to do now is to give you an overview. What is it, this memory management? So usually whenever you write a program, you have some static allocation. So you have this integer I, you write in your method, and then there is a space that is assigned for this integer, and you can use it. You can assign values to it. You can make calculations on it. This is called a static variable because you say in advance what variables you're going to need, and the space is known in advance. So this is called static allocations, but sometimes you want dynamic allocation. You have a linked list, you have some nodes, and you don't know how many of them you're going to need. Maybe you'll need 2, maybe you'll need 1,000,000. So you don't want to commit in advance to how many there will be, statically commit, and you want to dynamically allocate, and that's fine. So you just use malloc and you say how many bytes you need, and then you get a pointer to an area that was allocated for you, and you can use it. You can use this pointer and space as much as you want, and when you don't need it anymore, you say free the pointer, and this is called manual allocation. So why is it manual? Because you manually say, I don't need this anymore, you can free it. And soon we'll talk about automatic garbage collection where you don't need to say when you don't need it anymore. But if you look at this manual thing, it was the worst thing for the 80s, maybe, when programmers thought of the worst debugging thing. It was this memory manual allocation. So memory leaks is one thing, is when you forget to release, to free an object. You probably did that in your previous courses. I had once an application for email called Thunderbird by Mozilla. And maybe many years ago, it had a memory leak. And what happened is I was using it, and it became bigger and bigger through the day. And after 3 days, the system would stuck, nothing would run. And I had to open the list of processes and see that Thunderbird is taking all the space in the computer. I have to kill it. I open it again, and I can work for another 3-4 days until it fills again all the computer memory, and I have to kill it again. This is called the memory leak. So they forget to free an object, and they allocate, they forget to free, allocate, forget to free. Incrementally, this fills the memory. Eventually, you cannot work anymore. This is not easy to find. A lot worse bug is a dangling pointer. This is the other way around. You free it before you actually stop using it. So you free an object, and then the space is given to the allocator, and it allocates it again. But there is some other module in your software that is still modifying this space. So, and this is really terrible. This is really hard to find. This is a terrible bug. So if you if you run, eventually what's going to happen, there are two modules using this space, each of them writing to it something and reading, and eventually one of them is going to crash. Something is going to go wrong. When that happens, you have no idea where it comes from, because you have to go back to the time that you released it and you didn't mean to release it. And that happened a lot earlier in the execution. So it's really hard to find it. And these were like the most terrible bugs of the 80s until we had automatic memory management. Who knows what's today the most terrible bugs in today's environments? No one is working? Okay.
Like in memory safe, like buffer overflow?
No, I don't mean about memory. I mean in general, if you work today. So the most terrible bugs that happen today are with concurrency. It's when threads are running in various interleaving, and there is a bug that happens only once every 2 hours. And if you do any printing, it disappears. You don't see it. And it's terrible if you get into one of these bugs. But at the 80s, these were considered, there was no parallelism there, and they had this, and it was really terrible. And okay, so automatic memory management is when you say you allocate space for an object, but you don't have to free it. You just do with it something, and then eventually the system knows. So runtime reclaims an object if it knows the object will not be used anymore. Okay, and I'm saying knows with a grain of salt, because you don't know. You cannot tell. So this is what's called undecidable. You cannot tell. You will learn about it when you do chishuviyut, when you do computability. There's no way to tell if you're going to use it or not, this thing. So you have to be approximating this thing. You can show mathematically that you cannot tell if you're going to use an object again in your program or not. So if you cannot do this, what we usually do, this is the general solution, and this solution has been accepted because it works very well in practice. We say that if an object is reachable by a path of pointers from the original variables of the program, so a program has some variables in its methods, in global variables, and from it they can get into the heap. From the heap, each object has more pointers, so you could go by a path of pointers to various objects. If an object is reachable, then we say it's alive and the program is going to use it. Maybe it's not going to use it, but if it's reachable, we're going to keep it. If it's unreachable, there's no way the program can get to it, and there's no way it is going to be used subsequently. So if it's unreachable, then we can reclaim it. And this is like an approximation of liveness. So we don't really know if the object is going to be used, but we're saying if it's unreachable, we know it's not going to be used. So unreachable for us is going to be reclaimable. This is going to be for the rest of this semester. We're just looking for unreachable objects, and we want to reclaim them. This is our goal. Yeah.
What happened if we have like a linked list?
If I have a doubly linked list and it's unreachable from the program variables, for me, all of this linked list is unreachable and can be reclaimed. Okay? Yes, so I have to say reachable from what, right? It's reachable, a doubly linked list is reachable from itself, but it's not reachable from the program variables, if it's not reachable. If it's not reachable, then I can completely reclaim everything in that list. So I'll talk a bit more about from where it is reachable. There were other research saying maybe we can do better. Maybe something is reachable, but we're not going to use it anymore. And maybe I can reclaim it, but it never went into a real production system. So maybe the user can say this will not be used anymore. Maybe the compiler can find ways to discover that, but really this was never used in practice. So I'm not going to talk about it. Yes.
I have a question. If we are using branch predictability, can't we use something that's similar to it in memory as well? Because if we can predict branch jumps and so on inside, like.
Right. Yeah. I mean, it's a nice idea. So, and there was research about this. Like there were, I don't know, maybe 10 papers that tried to understand, what will happen in the program. But even if 90% of the branches are going to go that way, if you reclaim an object and somebody is going to use it afterwards because of the 10% or 1% even, then you're dead. This is you made the program crash. And so you cannot reclaim an object where there is even the slightest suspicion that this object may be used in the future. Yeah.
So automatic languages don't use compiler optimizations at all for memory. Like sometimes you can tell from the compiler if a variable goes out of scope or something.
Right. Yes. It could be done, and there were papers that showed that you can improve the identifications of reclaimable objects, but it was never. I've never seen it in a real industrial system used, because it was not. It so if you work in real industry, then you want your programs to be as simple as possible and as effective as possible. And there is this simplicity and effectiveness it's like a trade-off. So you don't want to make it a lot more complicated for getting a bit more effective. So it has not been adopted in real systems. Yeah.
When they allocated how it's implemented?
When does
Allocated the memory, so they use it need to allocate. Why isn't it implemented?
So the allocation happens here. When I say give me a new object, it's allocated. This is where the allocator comes, but there's no free. There's no place in the program where we'll say, free C, right? And therefore it's automatic. And but how is it done automatically? It's just by reachability. So we decide that something is reclaimable because it's unreachable. We can never get to it. Okay. So what's good about automatic garbage collection, memory management? So software engineering loves it. It relieves the user of bookkeeping. So, I don't need this anymore, but maybe some other component needs it. So I have to tell him, I don't need it anymore. If you don't need it anymore, and that one doesn't need it anymore, then we can reclaim it. But these are messages that are very hard to work with, and accounting that is really hard to work with. So if you have automatic memory management, you don't need this bookkeeping, and it's a lot better for software engineering. It's more reliable because you don't make mistakes if you don't do, right? If you don't have to decide when to free an object, you don't make mistakes about it. And so it's more reliable, the bugging is faster, you don't have all these memory bugs that were so hard for people in the past. And it's more understandable. The code is more natural and easy. You don't see if that thing does not need the object anymore and that thing does not need the object anymore, then let me free it. This does not appear in the program. It just there's no free. It just disappears when there's no need for it anymore. So it's very good for software engineering. And in Java, it's also used for security. I never give you a pointer to an object. You just have objects, and you cannot do bad things with the pointers, like treat them as different types of objects or do stuff with them. So from software engineering, this is really a good thing. And with languages, sometimes it's built in, like Java, C#, Lisp, Python. You have these memory managers that work automatically with garbage collection, And the programmer cannot free an object. You cannot say, free, this object, I'm not using it anymore. It's the job of the garbage collection. No one interferes with that. And sometimes it's an added feature. So you can take a program in C or C++ where there's no garbage collection, and you can download the library. Instead of doing malloc, you'll do GC alloc, GC for garbage collection. You do GC alloc, and then you don't need to do free. The GC alloc will also do garbage collection and free objects that are not needed anymore. So, and people really say that you can do this in like 20 minutes. You take a large project, you download this library of GC alloc, and you replace all your mallocs with GC alloc, you remove all the frees, and it just works. You have to be a little, you have to program nicely. You cannot do pointer arithmetic. You cannot take a pointer and add 8 to it, because this doesn't work with the garbage collector. But if you do it properly, then it's really easy to use it with C and C++. You can do it. And most modern languages are supported by garbage collection. So in the book, you will find a list of languages that were designed after 1990. And all of these are using garbage collection. So you see Python, PHP, Java, Haskell. I don't know which one you know, but those that don't, the new languages that don't use garbage collection, probably most of them you don't know. Maybe Silk is a research environment that does parallelism. Maybe you've heard about it, but most of it you probably haven't seen in practice. Okay, so memory is a major factor in program efficiency. The overhead in old Lisp system, Lisp was the first language that employed garbage collection, automatic memory management, and they had like 40% of the time was spent on memory management, which is really terrible. And in old Lisp program, they were started for artificial intelligence, and there were games written in Lisp, and you would play a game, and then it would stop and it would say garbage collecting as you're playing. And it was really bad. People did not like it. And today with Java, you get about 10% of the time going for memory management. You have to give it sometimes because you are allocating and freeing object. And this is really good. And you don't feel it. So there are no stops where it says, I'm garbage collecting, please wait. There are ways to do it, and we'll talk about these pauses that are, how do we prevent them? And techniques have evolved a lot since the 60s. So we'll talk about all this in the course. And we'll discuss memory management in the context of Java, but the idea is you can use them anywhere. So, but for us, we'll talk about Java to make it clear what we're talking about. Okay, so what is the setting? What's happening here? I have in the beginning, all the heap is unallocated. When the program wants to allocate a space, it allocates from allocated space, and it gets a space that is allocated and now in use by the program. Okay, this is the life cycle of a space. So it starts as unallocated, then it becomes allocated and in use by the program. And after a while, the program does not need this space anymore. And at some point, it also becomes unreachable because the program has written pointers, and now there is no pointer that's pointing to this space. So now it's allocated. It's still allocated. There's nowhere where it's written that it's not available, but it's unreachable. And the job of the garbage collection is to identify spaces that are allocated but now are unreachable and make them become unallocated again so that the allocator will be able to use them in future allocations. So this is the life cycle of a space. It starts as unallocated, the program allocates it, the program finishes using it, then the program makes it unreachable. And then when it's unreachable, the garbage collector can identify it and make it unallocated again so it can be used for future allocations. Questions about this? Okay, let me look at it from the point of view of the heap. So the heap initially is all unallocated, can be used for allocation completely, and I will color blue space that can be allocated. And then it starts allocating and using objects. And I will color in black things that are allocated and are in use by the program. And then after a while, it allocates a lot, but it also changes pointer, and some objects become unreachable. So everything now is allocated, but some of them are unreachable. White will be allocated but not in use, unreachable. And then the garbage collection comes and it takes all these unreachable spaces and makes them blue. It says to the allocator, these can be used for allocations. These become unallocated. So this is the picture. Yeah.
אנחנו ננסה לחבר את החלקים שהתפנו חזרה כחולים כדי לייצר יותר מקום בזיכרון, שזה כבר יותר מדי.
Right. This is a very good question. You have here two objects, two free spaces that are not together. So if I want to allocate something that is bigger, can I allocate it here? Somehow the allocator should know that there is space here that is free and not two spaces that are free. And this is going to be an issue. So usually when we'll talk about allocation and freeing, we'll talk about this. This is called coalescing of adjacent free spaces. Yes, it's a very good question. Okay, so I want to go into a break, but you forgot to ask about videos, right? I've never had this, that people don't ask me about videos. Maybe the English frightens you. Right? So I'm not going to publish previous videos, but I'm going to try and record what I'm saying here in class. But I'm not going to succeed all the time. So there will be talks that will be recorded, and then I will publish them for you. And there will be lectures that I will fail to record. And I will fail not because I want to fail, but if things do not work, then I will not take time. I will not take 5 minutes of the class time in order to work on the technical difficulties. I will give up. So the priority is going to be given to giving this talk to the class and not to working with the technology. So sometimes I'm not going to be able to record. When I can, I will record and publish it. And so this is going to be, don't trust it, but a lot of times you will have it. Okay, let's do a break and then 10 minutes is 33, 11:33. So you could be wondering how allocation happens and what and how it works, and we will have a full lecture about allocations in real, how it works very efficiently and so forth. But for the sake of having something in mind to work with while we're talking about garbage collection, I want to assume that we have a free list. So what does a free list mean? So we have all these unallocated objects that we are allowed to allocate from, and they will be, of course, in the heap, and I will mark them in blue. It doesn't matter, and there will be a free list pointer which shows us maybe the first element, but it doesn't have to be in order. There will be a linked list like that. So in this element, there will be the length of the element, so I know how much I have for allocation, and the next pointer. And this means the next, in the linked list, the next allocatable area. So all the blue things will be like that. There will be together in a linked list. And remember that this is not used by the program. This is space that I, as the memory manager, can use as I like. So I just put in here what I need, and I will have the ability to allocate just by maybe going to the first one. We'll talk a lot about how really we allocate, but I could go to the first one, and then I could check if I have enough space. If not, I could go to the next one and check if I have enough space, and so forth. So this is doable, and just for the sake of having something in mind to think about how allocation works, we'll have a more serious discussion on this after towards the end of the semester. Okay. So someone asked me, and this was strange to me, but it's clearly because I understand it too well. But someone asked me, how can I, if these things are unreachable by the program, how can I see them, reclaim them, identify them? They're not available to me as the program. And when we say we have to distinguish between the program and the memory manager. Okay, so the program cannot touch these spaces. It has no way to get to them. But the memory manager, it can touch anywhere it wants on the heap. It can do whatever he wants. So the program may be will be written in Java, and the runtime, the memory manager, everything that handles the program and runs it is going to be written maybe in C, in Rust, in any language you like. It will not be the Java heap. Like it will not be the Java program that has no idea where this project is, where this object is, and what's going on with him. Okay? So it's two different entities. Yeah.
If the runtime is not inside the operating system, how could it make sure that, like, if it runs on the same security level as the program, how could it make sure that the program?
So maybe think of it as we have like a space, memory space, okay? And the memory manager, this is really simplistic, but suppose the memory manager, and this is like run by maybe C. This is the C heap. And then there is someone who wants to run Java. So he allocates this huge space from which it's going to run the memory management for Java. Now, when the Java program wants to allocate, it maybe allocates for it, and then he can work on it. In a C program, it can see any byte it wants inside this space, and it goes and it looks here. There is a pointer. It looks here, and it has access to everything. So this could be the C heap, and this would be the Java heap. Okay, and so. And the Java itself can only touch objects that it can reach here. But the C can do whatever he wants with all this space. Okay, so this is something to note. And let's talk about the three classical algorithms for memory reclamation. You might have seen them in previous courses, but let's just make sure that we know what they are. So the garbage collection goal is to determine which objects are unreachable and reclaim these objects. This is what we're going to do the entire semester. There'll be lots of ways to do this right. And so objects are reachable from the roots. Okay, roots is a new terminology, this a new term that we're going to use. And the roots is all the local pointers that we have in our methods, the global pointers that we have in the program, maybe all kinds of weird stuff that's happening, like Java native interface is Java interface with C code that it may run, and it's allocating for that some space, and then the C may use this space. So there's all kinds of things that may be considered roots. We do not want to talk about it in this course. This is like an interface between the memory manager and the language, the compiler. So the compiler will tell us what are the roots, what can the program touch directly. We get that, and from that we do our memory manager. So in the book, I think there is a chapter that deals with what are roots and what are they really in practice. For us in this course, this is going to be orthogonal. There are some sets of pointers that the program can touch. Usually, most of them are just going to be in the runtime stack. These are the method frames, their local variables, these are the roots. But in general, it's just a term. We're going to say we're going to, whatever is reachable from the roots, we cannot reclaim. What is reachable from the roots, we will reclaim. Okay? And so from here on, we will just say roots. Okay? And the first method, the first classical method from 1960 is reference counting. So I'm going to associate a reference count with each object. And this count is going to check how many references point to the object. So if this is 0, I can reclaim the object. There's nothing, there's no way the program can get to it because there's nothing referencing it right now. So the program cannot get to it, so it's unreachable and I can reclaim it. So this is very simple and used in very simple systems. We'll have a full lecture about it because, okay, let's talk a bit about how it looks. So whenever I change a pointer from 01 to 02, when I allocate a pointer, the object gets a reference count 1 because I return a pointer to it. So there's one pointer to it. Whenever I change a reference to point from object 1 to object 2, I have to do two things. I have to increment the reference count of 02 and decrement the reference count of 01. If I do that, the reference counts become adequate. They become right. After I do this, after I change a pointer, maybe the reference count of 01 becomes 0. If it becomes 0, it's reclaimable. So I delete it. When I delete it, it has children. It may be pointing to other objects. If I delete it, I have to decrement the reference counts for all these objects because this is not going to be in the heap anymore. So I decrement the reference counts for all its children. When I do that, maybe more objects are becoming with 0 reference count and reclaimable. So I recursively go over all the objects that become 0. I decrement their children reference count, and I delete them if needed. So maybe there's a big tree in your, or big data structure in your program, and you just change one pointer, and it makes the root of this data structure become with reference count 0, and then you're going to recursively free all these objects. This is going to take a lot of time. So sometimes just changing a pointer will take a lot of time when you run your program. And again, I'm returning to what I said previously. It doesn't make the computer non-deterministic. It just, there is a reason why changing this root takes a lot of time to execute because it has to free and reclaim all these objects that have become unreachable. Okay?
Reference counter doesn't affect children?
No. I mean, the only thing that affects the children is if you become 0 and are removed from the heap. Otherwise, your children are not affected if you're still in the heap. Okay. So it took 3 years to discover that this cannot reclaim cycles. And you can imagine saying, how stupid people can be that it takes them 3 years to understand that. But it's not what this indicates. It indicates that no one used it, right? So no one noticed that cycles are not reclaimed. In the beginning, it was not very popular to use automatic memory management. It's very much not like today. So, but what does it mean that it doesn't reclaim cycles? If you have a cycle, even, just two objects pointing to one another, even if they become unreachable, you will never have a reference count 0 for these two objects because they point to each other. And this is true for cycles, and it's true in general for any strongly connected component that you've seen in algorithms, where each object can reach with a path of pointers any other object. Then even if this whole thing becomes unreachable, any objects there will always have reference count higher than 0. And so you'll never be able to reclaim a strongly connected component. And this is a problem, but normal programs, they said that most programs do not use too many cycles. As you see, this is very non-mathematically normal, and too many. But it is still true today. If you look at the benchmarks today that are used to evaluate execution times, you will see that many times they don't create a lot of cycles in the heap or strongly connected component in the heap. And then they could use other methods to, once in a while, they could collect cycles. Okay, and we'll talk soon about other methods that are not sensitive to cycles. They don't care if it cycles or not. They will reclaim everything that's not reachable. So, okay, so this is reference counting. During the years, there have been many improvements. Yes.
ספירה של הרפרנס זה מהתוכנית עצמה, נגיד אם יש לי שני פוינטרים לרשימה מקושרת, אז ללינק כזה לראש הרשימה. אז הלינק הבא יהיה לו 2 או יהיה לו 1
I only want to understand that I understand your example. So I have this linked list. I have 2 pointers pointing to the header. So this will have reference count 2, and this will have reference count 1. You just count how many references are pointing that specific object. You don't say, how many paths there are to reach this object from the root. Just that specific object, how many pointers. Yeah, I think he was wondering if I should write here 2 also, because there are 2 ways to get to this from the roots. Yeah, but no, you just look at the the direct pointers pointing to that specific object. Okay, so so you could use, okay, so during the years there have been many improvements, some of them done here but in the Technion. We'll talk a lot about that. There are cycle collection algorithms that we'll talk about, and in a separate lecture. Okay, so the second method is called mark sweep, maybe the most popular method. This was also in the 60s and in 1960, at exactly the same year. And it has 2 phases. There's a mark phase, where you just traverse from the roots. You traverse whatever is reachable from the roots. So you go through anything reachable and you mark it. You say, this thing is reachable. Okay, and after you've traversed everything that is reachable from the roots pointers, you go to a sweep phase where you just go over all objects in the heaps. And if it's not marked, then you know it's not reachable because you have gone through everything reachable and you've marked it. So there's the mark phase and the sweep phase. Okay, very simple. Here's a picture, for example. This could be the roots, maybe the stack, the runtime stack, maybe the registers. They point to stuff in the heap. You go from those that are pointed directly and you continue to traverse whatever is pointed from them. Some objects are not traversed and so are not marked. Here I marked them in black. Whatever is not marked can be reclaimed. So this is mark sweep. Any questions about mark sweep? Basic algorithm. If you have mark sweep, you're going to get fragmentation. So what happens is, say the black objects are objects that are alive, that are used by the program, and the yellow things are free to allocate. It could be that you have a lot of free space, but it's fragmented into multiple locations. And so if you have a large object, you have enough space to allocate it, but you cannot allocate it because you don't have consecutive space that could take it. So, and then there is a compaction. Compaction is going to take all black objects and move them to the beginning of the heap. We're going to have a lecture about that too. You need algorithms to do that. You move them all to the beginning, and then you have your space that you can allocate all these larger objects. Okay. And there will be a lot of compactors with all kinds of properties, and we'll understand what's good and what's not good, and how to do it in parallel, and so forth. Okay. Copying is the third algorithm that is considered classic and is used a lot. Copying, what it does, it partitions the heap into two spaces. Part one, the program works with and it just allocates everything in here. When that space is completely exhausted, the garbage collector comes, it traverses whatever is reachable and copies it to the second thing. Second thing is kept unused throughout the execution. It's free. You take everything that's traversed and copy it to here, and then you just start working on the second part, and the first part becomes reserved for the next collection. Okay, so this is how it looks. In the beginning, I only use part one, and then I copy, when I do garbage collection, I copy those that are reachable to the second part. Then I can work on this part, and this becomes reserved for the next cycle of garbage collection. Yeah. This is the space that I have. If I need more space, I will have to increase the heap. It's not. I cannot start allocating in the reserved space. So. Yes, you can decide to allocate more space. It's not easy, and you have to worry about how you do it. If you allocate more space, you also allocate it double than what you think you will need. Part of it will be used for this cycle, part of it will be used for the other cycle. Yeah.
Does it only work when the part is fully, like when it's full? Or
when do I start garbage collection? Yes, usually for us now, only when it's full. When we'll start talking about parallelism and concurrency, we'll do more complicated stuff. But right now, I only do it when it's full. Yeah. Okay. So the properties, you get compaction for free because you copy the allocated object, the reachable objects, you copy them to the beginning of the reserved space, and so they're just compacted. And but the major disadvantage is that half of the heap is wasted, and this is what bothered you. So you don't want to do it for a huge heap. The good things is you touch only the live object. So you don't have to go sweeping the entire heap. You just touch the live objects, you copy them, and then you just forget about the space that you've used so far. Okay, questions about copying? Cool. Okay, so there is here a table which kind of simplistically, like very, gives you some properties of all these algorithms, but all of this is basically wrong because it's looking at the naive algorithms, and all of them are going to become a lot more involved and with better properties. So I'm not going to go over it. You'll have it in your slides. You know, how much, what's the complexity of doing each of these algorithms? It will change. So we'll have different things as we go to more involved algorithms. And so I don't want to spend too much time on this, but you have this simplistic comparison if you want in the slides. Terms to remember from this introduction, you should know what heap is, what objects are. I think you know already. Allocate and free. Free is the same as saying deallocate, delete, reclaim. All these words are the same. We mean the same thing. Reachable, which I don't know if it's new for you or not, but reachable from the roots, and live is synonyms. It means the same for us. These are objects that we do not want to reclaim. Dead and unreachable are objects that we do want to reclaim. Roots is this abstract thing for us that are what the compiler says that the program can reach directly. And from it, we can reach objects in the heap. Reference counting, mark, sweep, and copying are the basic classical garbage collection algorithms. Tracing algorithms is mark, sweep, and copying because they trace all the reachable objects and they do something with them. Either they mark them or they copy them to the reserved space. So this is tracing, and fragmentation means that you cannot allocate because the available space is split. Okay, and standard terms that we're going to use, so benchmarks, I'm saying all the time, but I never said what it is. This is a set of programs that are used to evaluate. So if you do a new garbage collector, you will evaluate it on a set of programs to see if it's better or worse. This is something that the main, usually a benchmark suit is something that is set by the large companies in the industries. It's political, you know, each one of them wants to set something that looks like his major program to be a benchmark that everybody is evaluating their programs for, the hardware for, the software for, because they want the software to work better with their program. So, you know, Microsoft and Apple and Amazon, everybody would fight which programs would be included in the benchmarks. And but once a benchmark suit is determined, then this is used to evaluate everything you do, like garbage collection, operating system, whatever, you run them on benchmarks and see how they behave. Cache miss and cache hit, you should have seen in operating systems. This is very important. You have like a memory, you have the most recent things you touched in the memory in the cache. If you can get it from the cache, it will be a lot faster to get it, sometimes by a factor of 100. If you can get it from the cache, you can get it in one cycle of computation. If you need to go to the memory, it may take 100 cycles to get it from the memory. So cache miss and cache hits are going to be very important in actual life. Okay, the topics in this course. So we're going to spend lectures on these three basic algorithms. We're going to talk about compaction. For reference counting, we'll have to do cycle collection. That will also, each of them is going to be about a week. We're going to spend the week on allocations, understand, you know, the algorithms that are used today. There is what is called incremental. If I want to do my garbage collection in small pieces incrementally, it's going to be challenging. We're going to talk about it next week. And generations is something, basically all garbage collections today use this method. I will talk about it. We'll talk about it one of the weeks, and I will not go on here. Concurrency of garbage collection and snapshot, which they use this multi-core to become faster and shorten the pauses. We're going to spend weeks for that. Parallelism also in the same spirit. Cache conscience, hopefully we'll have time to talk about this. These things, I'm not sure we'll have time to go through, but we'll see as the semester proceeds. Impossibility is like that you cannot do stuff. You cannot do stuff too well. It's going to be a mathematical proof. Real-time is how we can do memory management if we have real-time requirements. Modern Java GC is what is used today, and maybe in the last talk we'll talk about this. Modern Java GC will be built of all the things we'll talk throughout the course, and then we'll say how they are used today. And challenges, all like the last things will happen if we have enough time to do them. But this is going to happen in the course. Okay, so let's start with market sweep. This is maybe the simplest algorithm, but let's talk about it for a bit. So it was invented by John McCarthy. Anybody knows the name? Okay, so he's one of the fathers of computer science. He worked in Stanford. So he died also about 15 years ago. He was, for example, the initiator of artificial intelligence. He got, so there's this Turing Award, which is the Nobel Prize for Computer Science. He got it in 71, which is approximately when your parents were born. So he's an old player in the field of computer science. So he was one of the initiators of artificial intelligence. He named it like that. He started the Lisp programming languages for artificial intelligence. And he was the one to propose Mark Swift. Also, he didn't get the Turing Award for that, but he also did that. He did time sharing. So initially, a computer could run one program and that's it. And he initiated the things that the same computer can have several programs share time on it. He did a lot of things. He's a very important father in the computer science domain. This is him talking in the conference in 2002. So he invented Mark Swift. Basically, you mark all objects that are reachable from the roots, and then you scan the heap and reclaim all unmarked objects. So in order to do this, you have to understand that each object always in any system has a header. So you ask the system to allocate 40 bytes, there will be more bytes allocated. You should understand that. It's not just the 40 that you allocate. For example, when you do free, you don't say how many bytes to free, right? You assume the system will know that there are 40 bytes to free. And this is written in the header almost always. This is like the length of the object is written in the header. So this is what you asked to allocate, and this is what the system added. And it has like the length of the object. If it's object-oriented programming, then you have the object class. So you'll know which fields are in the objects and where are the methods that you might operate on the object. Memory management would keep here a mark bit. Say this object might leave here a mark bit. There is sometimes in Java you can hash an object and then the hash value may be here. Locking may be kept here. There are lots of things that may be kept in the header. If the language is more sophisticated, more advanced, the header will play more roles in helping executing the program. Okay, so we have a header. And this will be for marking if we want. So how is it triggered? How do we start to do garbage collection? I mean, we only do new object and we never say now start garbage collecting. So what happens? So if there's no available allocation space while we're trying to allocate, then garbage collection is initiated. Okay? If we can allocate, then we just allocate and we return the pointer. If we cannot allocate, then we do garbage collection. This means the heap is exhausted and we are looking for space that's not reachable that we can allocate from. And so we run this mark sweep, for example. We could run copying or whatever we want. And if after executing the garbage collection, there's no available space, then we're screwed. We have to now return out of memory or do an exception or whatever our programming language dictates in this scenario. But this is how it works. So if you ask when is it triggered, how does it go, then this is how it goes. You allocate and there's no space. This is the standard beginning of a garbage collection. Okay, so what we assume here, and we will get rid of it in a few weeks, is that when you allocate and then run mark sweep, you do not do anything. So there is a pause in your program. And this could be very long. So you just allocated something. You allocated 100 bytes, and it could turn into something very long that gives you a pause in your program. So we'll do an effort to make this not pause the program, but be aware that this could happen. Okay, so here's the basic algorithm. I have mark sweep, and for all the pointers in the roots, which is the abstract thing that says what the program can directly reach, for all the pointers there, I mark them. And mark is a routine, is a method that I'll have to tell you what it does. And then I sweep, I go through the heap, and I will also tell you what I do. So what does mark do? Mark looks at the object and it says, if it is unmarked, then I will mark it and I will go for all its children and recursively call the same procedure on them. Okay, so this is like a traversal of the graph recursively. What happens, by the way, if I change the order? So I first go to all the children and recursively work on them, and only then I mark the object as marked.
I think you can mark some objects that are already marked. Maybe you mark them before you
No, I don't mark them. If I mark them,
change the order. So
get into a loop. That's the biggest problem, right? Okay, so think what will happen if I go to an object, I don't mark it, I go to the child, I don't mark it, and I go back to the first node, and then I will get into an endless loop. Exactly. So this will be the biggest problem here if I change the order. So I first mark it so that no one will trace it again, and then I go to the children to work on them. Okay, cool. So this is a recursive way to traverse all reachable objects from a given pointer. And I do it for any pointer in the roots. Okay, so, and then sweep. I go from the heap bottom and I go object by object, and any object whose mark bit is unmarked, I have not reached it in the mark procedure, I just free it. And then otherwise, I go to the mark bit and clear it to prepare it for the next cycle of garbage collection. So if it's unmarked, I free it. If it is marked, I clear the mark bit to prepare for the next collection. And then I jump over this object to look for the next object. So this is the sweep. Okay, questions on the basic algorithm? Okay, cool. So properties, it doesn't move objects, which is bad in the sense of fragmentation. There is one good thing about it, and that is that sometimes you do not know if you have a pointer or not. This happens in real life. If you're in C, for example, you have a cell, a word. It has something that may be an integer, maybe a pointer. You could conservatively say if there is some word that seems to be pointing at my object, I will not reclaim my object. Maybe it's reachable, so I will not reclaim it. But you cannot, if you wanted to do copying collection that moves object or compaction that moves object, and you have to change this pointer to point to the next, to the target address of where you move the object, then you have to know if it's a pointer or not. If you take an integer and by mistake change it because you thought it's a pointer, then you've destroyed the running of the program. So if you don't move objects, you can play conservative collection. And if you don't know if something is a pointer or not, treat it as a pointer. If you're moving objects, you cannot do this. So in real life, this is sometimes used for positive goals. Yeah.
Didn't you say that in Java, for example, you cannot handle pointers manually? So now language could
Again, this is confusing, but we have two entities here. There is the program who cannot do things, and there is the memory management who is powerful and can do anything. So he can look at pointers, he can do anything he wants with the system.
it could know exactly if it's a pointer or not.
So not really. So first in C, you cannot tell. There is like someone allocated space and then maybe put a pointer, maybe put an integer, you don't know. And even in Java, it's a lot more complicated when there's jitting happening while you run the program. So now something gets into a register and it is used, and then something else gets into a register. You're not sure how it happened. You know, it is copied from. The JIT is optimizing the execution to be very, very fast, but it does some shortcuts that you don't really know what's happening when you're just there running the low machine level code. So sometimes even in Java, you don't know what's a pointer and what's not. And then it's useful to do this. We're not going to talk about this anymore. In the book, I think there's a chapter about it, but we're not going to go on discussing this. So I'm just saying there could be a positive thing about not, not moving objects, which generally is bad because you get fragmentation. Complexity. So mark phase only touches the live objects like a copying collector, and the sweep phase touches all the heap. It goes through the heap, right? So, yeah, question.
But for the sweep phase, we do need to know on the heap what is an object and what is not, right?
Right. So all the objects have a very standard organization with a header, and you know everything that's happening there. When there is space that's not an object, what you should note is that you are responsible for it. Okay, it's part of your free list, of your unallocated space that you could allocate. And that space, you could do with it what you want. And what you do is you just keep it very, like we showed in the free list picture, you put a length of a space. It's not a real object, but it's space for you. You put the length and the next pointer. And so you can work easily with spaces that are unallocated because you, as the memory manager, decide how they will look. So you can go, when you go over all the objects, some of them are objects, some of them are free, maybe unallocated space, but everything has a structure. So you can work with it. Okay, so the complexity seems like live objects are a lot less than all the heap. But if you run measurements, you see that this is the dominant phase. This takes most of the time. Can anyone say why the mark phase will take more time than the sweep phase, although the sweep phase goes over all the heap and the mark phase goes only maybe over a third of the heap? Yeah?
But because the memory isn't contiguous, so it's not, you have pointers that are in different places.
And so?
You have to access cache misses. Yeah.
Cache misses, exactly, yes. So if I combine these two questions, yes. The mark phase is randomly, arbitrarily going in the heap. It goes to an object, there's a pointer, so it goes to the child, there's a pointer, it goes to another child, it goes arbitrarily in the heap, and each time it gets cache misses. Whereas the sweep, it goes very orderly over the heap. The architecture knows very well how to deal with it. And so there are a lot fewer cache misses. And so the sweep phase could be 20, 30% of the execution, although it seems to be touching more space. So termination is guaranteed because each pointer is traversed exactly once. This is something you will talk if, yeah, actually, you've seen algorithms, so you've seen BFS and DFS, it's terminating. This is maybe the most popular method today. Actually, copying is also a good competitor. And so at a more advanced implementation. So since this is so simple, I want to use this opportunity to talk about some engineering methods that are applied to this when it's used in practice in real systems. And you'll see what people do when they actually implement these things in the real world. I will talk about 4 things which are really done. There is something that has been taught in data structures a long time ago, and they're beautiful slides, but it's never done in practice. So I'm not going to include it, in spite of the beautiful slides. So let's see how much we can make it in this until we're out of time. So making the recursion explicit. So if you study maybe Introduction to Computer Science or data structures, then you think of recursion as a beautiful thing that's really nice to use. And but if you in practice try to do this, think for marking where you traverse all these graphs, and there could be bad graphs that will make your runtime stack become really, really large. And if it becomes really, really large, eventually it will say stack overflow and crash your program. So, and you have no control over it, right? As a memory manager, you do not know what's happening in the heap. That's the user has done. And so you're going to have a deep recursion with a space overhead of a frame, a stack frame for each of this level of recursions. There's a performance cost because you have to open a stack frame, copy all the registers that you need to save and stuff like that. There are potential crashes because the stack may be overflowed, and then what the user sees is stack overflow. It has no idea why it happened. It happened because of you, because the way you implemented Mark Sweep, and there's no way to debug such things. So this is really, really bad, and it is not used in practice. So I want to change this to be iterations that I control. So I do iterative loops instead of recursions. Okay, so what I use is I use a stack instead of the runtime stack. I have my own stack, which says what I need to traverse. So this is the original thing, recursive thing. It says for all pointers in the root, operate this recursive method. So I'm going to initiate my stack, the mark stack, and I'm going to say for all the objects that are references by the root, I'm going to mark them. I've seen them already. Each thing that I see, I mark. And then I put them in the stack in order that I will come back to them and look at their children. So whatever is referenced by the roots, I mark and I put it in the stack. Okay, and then I go into a second thing that's called mark heap. Okay, and then I will do the sweep. So how does mark heap look? So instead of this recursive thing, what I'm going to do is I'm going to look at my stack. If it has pointers to objects that I've seen, but I haven't looked at the children, I will take one of them out and I will handle it. How will I handle it? I will look at its children. And if a child is already marked, I need do nothing. But if it's not, if it's unmarked, that I'm going to mark it and add it to the stack. So I will later look at its children. Okay, this is what I do. So this replaces the recursion with iterations and the stack that I control. So you should see that now if I push something to the stack, where do? I do it here. If I push something to the stack and the stack is overflown, I don't have space to push, then I know that I've pushed something to the stack and I can say, stack overflow, I can work with it. I can do something. There are ways to overcome this, but here I know it. If I do a recursion, I don't ever know that this happens. It just happens during the runtime that the stack gets overflowed and I don't control it. Here, I know if I can push or cannot push if the stack is too full. So I can control it, which is a lot better. Also, the space overhead, I only push one pointer to the stack instead of a stack frame. So I need less space. And also, instead of calling a method to execute, I just push and pop from the stack, which is a lot more efficient. So this seems like a more complicated code than this, but it runs a lot faster. And this is what people would do in the real world. And question for you, what heap shape will cause the stack to grow the most? So as the memory manager, I just go over the heap and I just, traverse it. And the heap is controlled by the user of the Java program. I have no control over it. What would be the worst heap for me? Someone can imagine. Yeah. Okay, so the first, I think this is always the first suggestion, which seems very adequate. So I have this long linked list, but it doesn't work. So I'll tell you why. So here's maybe a root, and then I push this thing to the stack, and then the next time I come to the loop, I pop it, and then I push the second thing. Then I pop it and push the other thing. And so I just need one element in the stack for that. That seems like the worst case, but it's the best case. Binary tree can only have depth log n, and so this will make the stack at most log n. Yeah.
Maybe add another node to each.
Cool. Yes, exactly. So if I add here another node to each level, what will happen is I pop one, I push these two, and if I do it in the wrong order, I will leave this forever and pop this. I will push then these two, leave this forever, and pop this, push this. And so half of the nodes are going to stay there, and just the stack is going to contain half of the heap. This is a huge stack, which probably will create, you can try it if someone didn't do Java correctly, you can try to do mark sweep on this, and it will be probably have a stack overflow. But I don't think anyone does it in real production. Yeah. Root that? Right. That's an unfair example, but it's correct. You can say, so roots usually are limited and are determined by someone else. And usually we think of them as small, maybe 100, but not millions. But I could think of this. You could say there is a root, and then there is a huge array, which has lots of, that also works as a bad example, because when I go through this, I put all the children in the stack, and that will also be very large. But I really wanted this, so thank you for suggesting this first. Okay, and so we'll continue next week. Thank you very much. See you.